Hello students, this is Nikhilian, Assistant Professor, Department of Civil Engineering, AJT, Mangalore. In my previous session, I had discussed about limit state of collapse in shear. So in my previous session, I had explained you how the formulas are derived to calculate the maximum shear stress in a prestressed concrete member, and also I had explained you few of the examples. So today in this session, we shall continue the discussion on limit state of collapse on shear with few more examples. Okay, now let us consider today's first example. A prestressed I section has the following properties. Area is 55 into 10 to the power of 3 millimeter square. Second moment of area is 189 into 10 to the power of 7 millimeter to the power 4. Statical moment about the centroid is 468 into 10 to the power of 4 millimeter cube. Thickness of web is 50 millimeter. It is prestressed horizontally by 24 wires of 5 mm diameter and vertically by similar wires at 150 mm centers. All the wires carry a tensile stress of 900 Newton per millimeter square. Calculate the principal stresses at the centroid when a shearing force of 80 kN acts upon this section. So in this problem, the given member is of I section and the cross section area of I section is 55 into 10 to the power of 3 millimeter square, and here in this problem they have given second moment of area. So second moment of area is nothing but it is moment of inertia, and also they have given statical moment about the centroidal axis as 468 into 10 to the power of 4 millimeter cube. So when statical moment about the centroid is given, then the formula changes. So let us see that later. So hence it is I section, thickness of a web is given, thickness of a web is 50 mm, and the section is prestressed horizontally by 24 wires and the diameter of each wire is 5 millimeter, and also the member is also subjected for vertical prestressing. In vertical prestressing, they have used same cables of 25 mm diameter, and the cables or wires are spaced at a distance of 150 mm center to center, and all the wires carry a stress of 900 Newton per mm square. So for this we need to calculate what is the principal stresses at the centroid when the shearing force or shear force of 80 kN is acting at the support. So in our previous examples, what we were doing is we were calculating the maximum shear stress for at the support, and at the support we are calculating the maximum shear stress with respect to the centroidal axis of the support, that is we are calculating along the midpoint of the support. And here it is given that the statical moment about the centroid is 468 to the power of 4 millimeter cube. So when this value is given, or when they ask us to calculate the shear stress at a certain distance above or below the centroidal axis, then we should use this formula, that is V by IB into A into Y bar, where A Y bar or A Y dash is the statical moment about the centroidal axis. So this formula is used when the value of a statical moment about the centroidal axis is given, and when they ask us to calculate the shear stress at a certain distance above or below the centroidal axis. So here in this equation we know what is V. V is shear force. So shear force is given in the question, it is 80 kilonewton. I is moment of inertia. So moment of inertia is given. Second moment of inertia is 189 into 10 to the power of 7 millimeter to the power 4. B is width of the section. So width of the section is given, that is 50 millimeter, and a y bar or a y dash is given, it is 468 into 10 to the power of 4 millimeter to the power cube. So substitute the values of all this, we will get 3.95 Newton per millimeter square. Therefore, the maximum shear stress developed in the section is equal to 3.95 Newton per millimeter square. So again I will tell you, so we will use this formula to calculate shear stress when statical moment about the centroidal axis is given, or when they ask us to calculate the maximum shear stress above the centroidal axis or below the centroidal axis at the support. And we know what is the formula to calculate the maximum principal stresses along the diagonal of the section. So this is the formula to calculate the maximum and minimum principal stresses. So in this formula, we should calculate what is f of x, what is f of y, and what is tau v square. And here we have calculated what is tau v. So tau v is the maximum shear stress, and that is 3.95. We have calculated in the first step. And now, what is f of x? So at the support, f of x is equal to p by a. Therefore, horizontal prestress at centroid, or horizontal prestress at centroidal axis of the support, that is equal to p by a. So if you see in the question, they have not given what is the prestressing force. So they have given all the wires carries a tensile stress of 910 per mm square, and the diameter of wire is given and number of wires are given. Therefore, using number of wires and diameter of wires and tensile stress acting in the wire, we can calculate what is the pre-stressing force that is applied to the cable. We know that stress is equal to load by area. Therefore, load is equal to stress into area. So in the question, they have given the values 24 wires and 5 mm diameter. So using this diameter of a wire, we can calculate what is the area of a single wire. Therefore, for 24 wires, what will be the area? So 24 into 19.7 into 900. So 19.7, it is the cross section area of a single wire. That is pi d square by 4, which is equal to pi into 5 square divided by 4. We will get 19.7. So 19.7 is the cross section area of a single wire, and 24 is the total number of wires. So 24 into 19.7, this is the area of a cable, and 900 Newton per mm square is the tensile stress acting. So area into stress, which gives us initial pre-stressing force divided by area of a section. So area of a section is given, that is 55 into 10 to the power of 3 millimeter to the power of 2. So substitute the value of area here in the denominator. We will get horizontal pre-stress at the centroid, which is equal to 7.75 Newton per mm square. Therefore, f of x is equal to 7.75 Newton per mm square. Similarly, here they have given that the member is also subjected for vertical prestress. So in vertical prestress, they have given same wires are used, like 24 wires are used, and diameter of the wires are 5 millimeter. But they have given here the spacing of a wire is 150 mm at center to center. So here we should calculate f of y. So to calculate f of y, we use this equation. So see here, stress in the steel, Fs, diameter of the steel wires, thickness of a web of a flanged section, and spacing is of a steel is given. Then transverse vertical prestress can be calculated using the equation f of y is equal to f of s into pi d square by 4 into t w into s. So in the question they have given what's the stress in the wire, they have given the diameter of a steel wire, they have given thickness of the web, and the spacing of a wires is also given. Therefore we can use this equation to calculate what is the value of f of y. So in the numerator it is P into A, that is prestressing. Prestress in the wires it is 900 Newton per millimeter square, and area of a wire, area of a single wire is 19.7, that is diameter is 5 millimeter. If I calculate the area using equation pi d square by 4, I will get 19.7 millimeter square. So in the denominator it is 150 into 50, where 150 is the spacing and 50 is the thickness of web. Therefore vertical pre-stress f of y is equal to 2.46 Newton per mm square. So we have calculated what is f of x, that is 7.75 Newton per millimeter square. We have also calculated f of y, that is 2.46 Newton per millimeter square. We have calculated shear stress at the support, that is 3.95 Newton per millimeter square. Now to calculate maximum and minimum principal stresses along the diagonal of a section. So we have the equation f of x plus f of y by 2 plus or minus 1 by 2 into square root of f of x minus f of y whole square plus 4 into tau v square. So already we have calculated the values of all these terms. So substitute the values of these terms, we will get the final answer as 5.1 plus or minus 4.7. If I consider this as a plus, then it is 9.8. If I consider this as minus, then it is plus 0.4 Newton per mm square. So here if we observe the values, here it is 9.8 and it is plus 9.8, and here also it is plus 0.4. So plus means the stresses in the member is compressive stresses. Therefore the minimum as well as maximum stresses developed in the section is compressive stress. Therefore the principal tension is completely eliminated due to vertical pre-stressing. So there is no principal tension or diagonal tension developed in the member due to the application of vertical pre-stressing. So in our previous examples we were getting the maximum value as positive and minimum stress value as negative. So that was indicating that when we consider minimum and maximum, there was a tensile stress developed in the member along the diagonal, because in our previous examples we didn't consider the vertical pre-stressing, whereas in this example we have considered the vertical pre-stressing. So as a result of this vertical pre-stressing, the diagonal tensile stress is completely eliminated. So that is the advantage of vertical pre-stressing. Let us consider the next example. A cantilevered portion of a prestressed concrete bridge with a rectangular cross section 600 mm wide and 1650 mm deep is 8 meter long and carries a reaction of 350 kN from the suspended span at the free end, together with a uniformly distributed load of 60 kN per meter, which includes of its own weight. The beam is prestressed by 7 cables, each cable carrying a force of 1000 kN, of which 3 are located at 150 mm, 3 at 400 mm, and 1 at 750 mm from the top edge. Calculate the magnitude of principal stresses at a point 550 mm from the top of a cantilever at the support section. So in this problem, it is a prestressed concrete bridge. So the bridge is a cantilevered portion. The span of a cantilevered portion bridge is 8 meter long. The cross section is of a rectangle section, and the cross section is 600 mm by 1650 mm. And here the member is subjected to a UDL of 60 kN per meter, and this 60 kN per meter includes live load and dead load. Along with this 60 kN per meter, there is a point load of 350 kN, right? There is a point load of 350 kN, and this 350 kN point load is acting at a distance of 8 meter from the fixed end. That means the point load 350 kN is acting at free end of a bridge, and this beam is pre-stressed with 7 cables. Out of these 7 cables, 3 cables are located at a distance of 150 mm from the top. Next, 3 cables are located at a distance of 400 mm from the top, and 1 cable is located at a distance of 750 mm from the top edge. And each cable is pre-stressed by a force of 1000 kilonewton. The 7 cables, there are 7 cables, and each cable is carrying a pre-stressed force or a pre-stressing force of 1000 kilonewton. And for this beam or for this member, we need to calculate the principal stresses at a distance of 550 mm from the top edge at the support section. In our previous examples, what we were doing is we were calculating the principal stresses at the support with respect to the centroidal axis of the support. But here in this problem, they have asked us to calculate the principal stresses at a distance of 550 mm from the top edge of a beam. See, consider a beam, a rectangular beam of a depth 1650 millimeter, and width of the beam is given, it is 600 millimeter. So it is a rectangular beam, therefore y1 is equal to y2 is equal to d by 2. So d by 2 means it is 1650 by 2. Therefore the centroidal axis lies at a distance of 825 millimeter. So this is the centroidal distance, which is at a distance of 825 millimeter from the top edge, as well as at a distance of 825 millimeter from the bottom edge. So let us consider the first 3 cables. So the first 3 cables are located at a distance of 150 mm from the top edge. So this first 3 cables are located at a distance of 150 mm from the top. Second 3 cables, these 3 cables are located at a distance of 400 mm from the top edge. So from here to here the distance is 400 millimeter, and one cable is located at a distance of 700 mm from the top edge of a member. So this is the last cable, which is located at a distance of 700 millimeter from the top edge. From here to CG of the cable, the distance is 700 millimeter. And what they have given is we need to calculate the principal stresses at a distance of 550 millimeter from the top edge. So from the top edge we need to calculate the principal stresses at a distance of 550 millimeter. So 550 millimeter means it is here, so we should calculate the stresses acting along this plane. So this plane is at a distance of 550 millimeter from the top edge. So we should calculate principal stresses along this plane. In our previous problems, we were calculating the principal stresses along the centroidal axis. That is, we were calculating the principal stresses along this plane. And now it is being asked to calculate at along this plane at a distance of 550 mm from the top. So let us consider the depth 550 mm in the as a shaded portion. So let this shaded portion be 550 mm, where we need to calculate the principal stress. So here in this section the cables are at different depths. The cables are located at depth of 150 mm, 400 mm and 700 mm with respect to the top edge. So first we should calculate where the CG of all this cable lies. So first we should calculate the centroidal axis of the cable. So centroid of the prestressing force from the top edge. So centroid of the prestressing force is nothing but we are calculating centroid of the cables with respect to the top edge. So I am calculating the CG of the cables with respect to this edge. So 3 into 150. So first 3 cables. So these 3 cables are located at a distance of 150 mm from the top edge, therefore 3 into 150, and second 3 cables are located at a distance of 150 400 from the top edge. So that I have substituted here. So 3 into 150 plus 3 into 400, that is second 3 cables at a depth of 400 mm from the top edge plus 1 into 750. So one cable which is located at a distance of 750 mm from the top edge divided by 3 plus 1 plus 1, that is 3 plus 1, 3 plus 1 is total number of cables, that is 7 cables. So y is equal to 343 millimeter. So CG of a cable is laying at a distance of 343 millimeter from the top edge. So with respect to this top edge, the CG of all these cables are laying at a distance of 343 millimeter from the top. So from the top 343 means it may come somewhere here. So at this point the centroid of a cables are present. Then what is the eccentricity of the cable with respect to the centroidal axis? So we know that centroidal axis is located at a distance of 825 mm from the top edge, and the CG of a cable is located at a distance of 343 millimeters from the top edge. Therefore eccentricity of the cable is equal to 825 minus this distance, that is 343 distance. So 825 minus 343, therefore eccentricity is equal to 482 millimeter. So here is the CG of a cable which is at a distance of 343 from the top edge, and from here to here it is the eccentricity. So eccentricity is the measure between centroidal axis and CG of a cable. So that distance from here to here where the CG of cable lies, this distance is the eccentricity. So this from here to here the distance is equal to 825 minus 343, so that is equal to 482 millimeter, that is the CG of a cable. So pre-stressing force P is equal to 7000 kilonewton. So we have 7 cables, 7 cables, and each cable is carrying a force of 1000 kilonewton. Therefore total force acting along the member is equal to 7 into 1000, which is equal to 7000 kilonewton. So moment on the section due to pre-stressing force. So this you should remember. In our previous examples, we have not calculated the moment on the section due to pre-stressing force, but here we are calculating the moment on the section due to pre-stressing force. So this is because, see here, we are calculating the principal stresses at a point of 550 mm from the top edge. So we need to calculate what is the moment. In our previous examples, we were calculating principal stresses along the centroidal axis. Along this centroidal axis, we were calculating the principal stresses in our previous examples. But in this present example, we need to calculate the principal stresses along this plane. So when it is away from the CG of a section, we need to calculate what is the moment developed in the member due to pre-stressing force. And here the formula for f of x changes. So at the support and at the centroidal axis, the formula for f of x was p by a, whereas here for this, to calculate the value of f of x for this plane, the formula will be this one. So to calculate the principal stresses with respect to a depth of 550 mm from the top edge, then f of x is equal to p by a plus p into e by I plus m by y, m into y by I. So this formula we need to use. So we are going to use f of x is equal to p by a when we are calculating the principal stresses along the centroidal axis. So away from the centroidal axis, we should use this formula to calculate what is f of ex. So remember this formula, f of x is equal to p by a plus p into e by I plus m into y by I. So here it is plus or minus m into y by I depending upon the type of bending moment. Therefore, a moment induced in the section due to prestressing force P into E is equal to 7000 into 482 millimeter. So 482 millimeter is the eccentricity, which is converted into meters. It is 0.482 meters. Therefore, moment induced in the section due to prestressing force is equal to 3374 kilonewton meter. So next, to calculate what is the moments induced due to external loads at the support. So it is a cantilever beam. So see the loading condition of a beam. The beam is subjected to a UDL of 60 kN, which includes its own weight as well as live load, and it is also subjected to a point load of 350 kN at its free end. So to calculate the moment, we know that the maximum moment occurs at the support. So there is a point load of 350 kN at the free end. The moment of that free, the load which is acting at free end is 350 into 8 plus the bending moment due to live load and dead load, which is in the form of UDL, is WL square by 2. So W is 60 into L square. 8 square is 64 divided by 2. So WL square by 2 is the equation to calculate the maximum bending moment in the cantilever beam. Therefore, the bending moment or moment which is induced in the section due to live load and dead load is equal to 4720 kilonewton meter. So again I will tell you, 350 into 8, this is the moment due to the point load which is acting at the free end. So 350 is the point load acting at the free end, and 8 meter is the distance of the point load with respect to the support. And we know the maximum bending moment in a cantilever beam occurs at the support. Plus 60 into 64 by 2, it is W L square by 2. So W is 60 kilonewton per meter, which is in the form of UDL and which includes live load and dead load. 64 is the length, that is 8 square W into 60 into 8 square by 2. So 8 square is 64. Therefore total bending moment due to point load and UDL is equal to 4720 kilonewton meter. Maximum shear at the support. So now to calculate the shear force at the support, there is a point load at free end, that is 350 plus shear force due to UDL. UDL intensity is 60 and length is 8. So 350 plus 60 into 8. Shear force, maximum shear force at the support is equal to 830 kilonewton. So 350, it is the point load which is acting at the free end, and the intensity of the live load and dead load, which is in the form of UDL, is 60. So 60 into 8. 60 into 8 is the shear force due to UDL. 350 plus 60 into 8, which gives 830 kilonewton. So 830 kilonewton is the maximum shear force developed at the support. second moment of area, that is moment of inertia, I is equal to BD cube by 12. So it is a rectangular section. For a rectangular section, to calculate moment of inertia or to calculate second moment of area, we have formula BD cube by 12. So B is 1000, sorry, B is 600 millimeter and D is 1650 millimeter. Therefore, I is equal to 600 into 1650 millimeter cube by 12, which gives 225 into 10 to the power of 9 millimeter to the power 4. So this is the moment of inertia. Then to calculate resultant stress at 550 mm from the top edge of the support section. So here resultant direct stresses is nothing but f of x. So f of x, the formula is fx by a plus p e by I plus or minus my divided by I. So p by a, p into e. So here it is minus because it is a cantilever beam. Therefore, the moment induced in the cantilever beam is always negative bending moment, or it is always a hogging bending moment. Therefore, this when we substitute it will become minus 4720. Hence, here the sign is minus. So m into y. So y is 275. So 275 is nothing but 275 is the distance of the plane along which we need to calculate the principal stress. So we need to calculate the principal stress along this plane. So this plane is laying at a distance of 550 mm from the top edge, and with respect to the centroidal axis of the member, this plane is lying at a distance of 275 millimeter. Therefore, y is equal to 275 millimeter. So I will tell once again. Here y is equal to 275 millimeter because we are calculating the principal stress along this plane, which is laying at a distance of 550 millimeter from the top edge. Then from the centroidal axis, this plane is laying at a distance of 275 millimeter, which is equal to y. So here substitute the value of y is equal to 275 millimeter, and 225 into 10 to the power of 6 is the moment of inertia. So this is 225 into 10 to the power of 9. So this should be 9. So calculating this, we will get 545.43 Newton per millimeter square. So f of ex, direct stresses, is equal to 543 Newton per millimeter square. Then what is the maximum shear stress at 550 millimeter from top edge of the support section? So along this plane, what is the maximum shear stress? So to calculate the maximum shear stress, that is tau v, we will use this equation. So already I told you in the previous example, when a static moment of a section is given, and when we are calculating the principal stresses away from the centroidal axis of the section, we should use this formula. So here also we are calculating the principal stress along the plane which is away from the centroidal axis. So we are using this equation of V by IB into A into Y bar or Y dash. So V is 830 into 10 to the power of 3, which we have calculated, that is a shear force 350 plus 60 into 8, which is equal to 830 kilonewton, and here it is 830 into 10 to the power of 3, which is converted into Newton. I is moment of inertia 225 into 10 to the power of 9 into width of a section is 600 millimeter into area of a section 600 into the area. This is the area of the section where we are calculating principal stresses. So 600 into 550. So we are calculating the principal stress along this plane. Therefore, we should consider this area. We should consider the stresses developed in this area, this shaded portion. Therefore, the area of this shaded portion will be 600 into 550 mm. 600 into 550 mm. That is what it is substituted here. 600. A is 600 into 550 mm, and y dash it is 550 by 2. So here it is typing mistake. It is 550 by 2. So 600 into 550 into 550 by 2, which gives 1.1 Newton per mm square. So 1.1 Newton per mm square is the maximum shear stress developed along this plane. So next, to calculate maximum and minimum principal stresses. So here in this case, there is no vertical prestressing. Therefore, the term f of y will be eliminated. Therefore, the final formula for calculation of maximum and minimum stresses will be f of x by 2 plus or minus 1 by 2 square root of f of x square plus 4 into tau v square. So substituting the values of f of x and tau v. So f of x is 5.43, which we have calculated here. So 5.43 by 2 plus or minus 1 by 2 square root of f of x square. It is 5.43 square plus 4 into 1.1. So this 1.1 is maximum shear stress at the support. So shear stress at the support we have calculated in the previous step, that is 1.1 Newton per mm square. So substituting the value, we will get what is the minimum and what is the maximum principal shear stress developed along the support. So the maximum principal stress is 5.67 Newton per mm square, and minimum principal stress is minus 0.21 Newton per millimeter square. So the maximum principal stress, it is compressive in nature, and minimum principal stress, it is minus 0.21, which is tension in nature. So this is how we will calculate maximum and minimum principal stresses for a pre-stressed concrete members. So here what you should remember is, what's the formula to calculate the maximum shear stress when it is along the centroidal axis, and what is the formula to calculate shear stress when it is away from the centroidal axis. So these two conditions you should remember. And also you should remember what is the formula to calculate maximum and minimum principal stresses when vertical pre-stressing is given and when vertical pre-stressing is not given. So these are the things you should remember to calculate the maximum and minimum principal stresses along the pre-stressed concrete members. And now let us move to the next part of the same module, that is ultimate shear resistance of prestressed concrete members. So in previous topic we were calculating what was the maximum and minimum principal tension developed in the member, and here we will analyze the given section and we will calculate what is the maximum shear resistance of a prestressed concrete member. And here the analysis is done by considering two conditions. That is, we will consider what will be the shear resistance of a member when the member undergoes shear cracks, and what will be the maximum resistance of a shear when the member undergoes flexural shear cracks. So in a prestressed concrete member, we have two types of shear failures. That is, failure due to web shear cracks and failure due to flexural shear cracks. So these are the two modes of shear cracking in the PSC members. So in this picture you can see the cracks. So these cracks are called as web shear cracks, and this type of cracks are always developed at the supports, and flexural shear cracks are developed at the midpoint where the bending moment is maximum, and it is developed due to shear force or the vertical reaction. These cracks are developed due to shear force or vertical reaction, and these flexural shear cracks are developed due to the flexural action of a beam or moment of a beam. So we are going to analyze a given beam and we will calculate what will be the maximum shear resistance or maximum shear capacity of a beam when the beam undergoes a web shear failure or flexural shear failure. So let us see what is flexural failure due to web shear cracks. When the principal tensile stresses exceeds the tensile strength of the concrete, web shear cracks are developed from an interior point, and web shear cracks develop in highly prestressed beams with very thin webs and in the beams subjected to large concentrated loads near a simple support. The ultimate shear resistance of a prestressed concrete section with web shear cracking is governed by the limiting value of principal stress developed in the concrete. And the second failure is failure due to flexure shear cracks. When the combined shear and flexural tensile stresses produces a stress that is produces a principal tensile stresses and that exceeds the tensile strength of the concrete, flexural shear cracks are developed by flexural cracks in the inclined direction in the members without shear reinforcement. The inclined shear cracks extend to the compression phase, resulting in sudden explosive diagonal tensile mode of the failure. So these are the two modes of shear failure in the prestressed concrete members. So we should analyze a given prestressed concrete members for these two modes of failures. Now let us see what are the formulas used to calculate the ultimate shear resistance of the concrete in web shear cracking. So here let us see the formula to calculate the maximum shear strength of a prestressed concrete member by only considering shear cracking. That means we are not going to consider the cracks which are induced due to flexural action. And these formulas are given in page number 46 of IS 1343 1980. So remember this, the formulas to calculate the maximum shear strength of a member under web shear cracking is given in page number 46 of IS 1343 1980. So first let us consider the first condition. What will be the ultimate shear strength of a member when the cables provided are straight cables? So when the straight tendons are provided, VCW is equal to VCO is equal to VC is equal to 0.67 BD square root of FT square plus 0.8 FCP into FP. So here VCW or VCO or VC, which is nothing but it is the ultimate shear strength of a prestressed concrete member. B is nothing but width or breadth of a rectangular section. B or BW, it is width or breadth of a web in a flanged section when we consider the flanged sections. D, that is a capital D, is the overall depth of the member. FCP is equal to F of X, so which can be calculated by P by A, which is compressive stresses at centroid of the section, and Ft, it is the tensile strength of the concrete, which can be calculated by 0.24 square root of Fck, where Fck is the compressive strength of the concrete. So the second condition is when inclined or curved or parabolic tendons are provided. So the first condition was when straight tendons are provided, what will be the ultimate shear strength of a member under shear cracking, under web shear cracking. And the second condition is when inclined or curved cables or parabolic cables or tendons are provided, then what will be the ultimate shear resistance of a prestressed concrete members in web shear cracking. So that is VCW is equal to VCO is equal to VC is equal to 0.67 BD square root of FT whole square plus 0.8 FCP into FT plus neta P sin theta, where neta P sin theta is the vertical component of vertical prestressing force, neta is loss ratio, P is prestressing force, and theta, or it is also called as alpha, which is equal to 4h by L into 180 by pi. So here if we multiply by 180 by pi, then theta or alpha will be in terms of degree, whereas in the calculation of the inclination of a cable while solving the problems, usually we will keep the values of theta or alpha in terms of radians only. Hence we can use the formula for calculation of theta or alpha as 4h by L, and FCP is equal to f of x, which is equal to px by a, where px is equal to p cos alpha by a. Again, p is the prestressing force, alpha is the inclination of the cable or slope, a is the cross section area of the section. Therefore FCP is compressive stresses at centroid of the section. So these are the two formulas which you should remember for the calculation of ultimate shear resistance of a concrete under web shear cracking. So this is for straight tendons and this is for inclined or curved tendons. So these two formulas are given in page number 46 of IS 1343-1980. So in some of the textbooks they have considered the different formula. So let us see what is the different formula that they have given in some of the textbooks. Note, so ultimate shear resistance can also be determined using the below given formulas. So when the straight tendons are provided, ultimate shear resistance VCW or VC is equal to B into I by S square root of Ft square plus Fcp into Ft, where I is second moment of the area or moment of inertia, and S is statical moment of the section above neutral axis taken about the centroid, where S is equal to A into Y bar. And when the cables are inclined or parabolic or curved cables, then VCW is equal to VC is equal to B into I by S square root of Ft square plus Fcp into Ft plus neta P sin theta. The value of I by S varies from 0.67 D for a rectangular section to 0.85 D for a flange section. So the difference between these formulas and previous formulas is only this term. So here it is given as 0.67 BD and here it is B into I by S. So the value of this I by S varies from 0.67 D to 0.85 D. So this is the only difference between this formula and this formula. So it is better if you remember both the formulas, and the formulas is available in page number 46. So remember the page number 46 of IS 1343-1980. Okay, so previous one was the formula which is used to calculate the ultimate shear resistance or ultimate shear strength of a prestressed concrete member when it is subjected for web shear cracking. And there is one more failure, that is failure due to flexural shear cracking. So what will be the ultimate shear strength or maximum shear capacity of a prestressed concrete member when it is subjected to flexural shear cracks? So analysis of failure due to flexural shear cracks. So this formula is given in IS 1343/1980 in page number 46 clause 22.4.2. So if you go to page number 46 of IS 1343, you can find the formula for both for flexural shear cracks as well as for web shear cracks. So remember page number 46. So the formula to calculate the ultimate shear resistance of a prestressed concrete member under flexural shear crack is VCF is equal to 1 minus 0.55 FPE by FP tau C BWD plus M naught by M into V. So it is given in the code book, so no need to remember the formula. It is sufficient if you remember the page number and clause, where FPE is effective pre-stress after all losses which shall not be put greater than 0.6 FP. FP is characteristic strength of pre-stressing steel. Tau C is ultimate shear stress capacity of concrete compiled in table 8.1. BW, width or breadth of member, which for flanged section shall be taken as breadth of the web. So remember this condition. BW, it is the breadth of the member when a flanged section is given, or when we need to calculate the shear resistance of a flanged section under flexural shear condition. We should consider breadth of the web as BW. So D is effective depth to the tendons, or it is the effective depth of a section. M naught is moment necessary to produce stress in the concrete at the extreme tension fiber. M naught is to be calculated as 0.8 into FPTI divided by YB, where FPT is the concrete compressive stresses at the extreme tension fiber due to effective pre-stressing force. I is moment of inertia and YB is the distance of extreme tension fiber from the centroid for beam section. V and M is shear force and bending moment respectively at the section considered due to ultimate loads.